possible to allow me share screening because it says that host disable participant screen sharing? Thank you.
No, we will wait for 5 minutes. We'll have a small introduction, and then
Okay.
I will make you the host so that you can share. No issues.
Excellent. Okay, that's absolutely fine.
And Jenkins, shall we start?
Yes, sir. I think we can go.
Welcome, participants. I welcome the people from different parts of the world. So we have a change in the timing today. Still, you people are ready to hear more from our FDP. And this is the last day of the FDP. But remember, research doesn't have any last days. It is a lifelong experience, and you have to learn every day new concepts. So before going into the agenda of today's session, I will like to give you two important aspects about the participants' interaction on yesterday's session. So one is you may be feeling why image deep learning, the concept of deep learning should revolve around image. Why not other data? The simple answer is, as long as human beings have eyes, images will be there. As long as human beings have brain, processing or machine learning will be there. Eyes and brains are very much related to each other. God created human beings in his own image. And now human beings are trying to create something in their own image. So when they create something in their own image, the important body part which captures data from the environment is eye. We have 5 sense organs. Among the 5 sense organs, these eyes are going to play a major role in giving the data to the brain. Their rough calculation says around 83% of the data from the environment to the human brain is via eyes. That's why images are very, very, very important. But we need to find some innovative contribution in the area of image processing, which is always very much blended with deep learning and machine learning applications. That doesn't mean that all our other sensors you have only deep learning models, you have 3D learning models, where you have any number of data associated with them. But images play a major role in that. The second one I want to give you a challenge or a food for thought is, yesterday when Dr. Utku was sharing his presentation, if you observe closely, most of the people are saying that your deep learning models are going to detect the objects based on the shapes. That is 100% correct. So when you are recognizing a car, you can do it because you have a shape, lines and squares, banners, everything will come into picture. And when you want to distinguish a human being and a cat, again, it is possible. All these stuffs are okay. When we go into a medical image concept, if you closely observe all the 4 presentations, you can see that they are trying to say whether it is normal or abnormal. So whenever you go for abnormal images, you have some difference in the shapes, right? But my question is, there are some medical images where there are some subcategories within the abnormal images. Say, take for example, the brain tumors. You have glioma, metastasis, meningioma, and astrocytoma, more common in Indian people. So when you take these 4 categories, they can occur in any shapes. They are not dependent on the shapes. The only thing by which we can differentiate is the intensity. Now my question is, if we give such type of images to deep learning models such as CNN, how will it work? Will it be a successful one when it is shape independent? When it is a successful one, it is interesting to see the outputs of the convolution layers, the features. What are the features it is trying to give? These are the 2 questions I think the researchers who are sitting on the other side can take over, which will be very challenging. And when you look at the research papers, 99% of the research papers are going into the concept of pattern classification, right? With normal or abnormal, something like that. But papers in these concepts are very, very rare. Maybe someone can explore that. So coming to the last day, we'll have a presentation from the speakers. Today we have 2 speakers. And after the presentation, we are interested in having you to give a feedback, a live feedback, which is purely voluntary. If you feel like you can share something, you can come and share after the presentation and the question and answer session. Then we'll go into the official vote of thanks and close this FDP. So this is the plan for today's meeting. And today we are having two eminent speakers from the UK. I remember my quote when I studied the history subject: "The sun never sets in the British Empire." These are the famous lines still I remember, right? So the research is very popular, and most of the professors and young academicians are into research in UK. And today we are very much thankful to two such people, Dr. Anastasia and Reda. And these people are having a close association with me. We are very much interested in having collaborative works in the form of publications and editorial works, and specifically projects. We are into a project called as Intelligent Transportation System using machine learning and deep learning. And Reda is our project research associate. So this team definitely is going to give you another dimension of deep learning and machine learning. Now I request Dr. Jenkin to give a brief introduction about Dr. Anastasia and Mr. Reda.
Yeah, thank you, Professor Jude. An Irish playwright, George Bernard Shaw, writes like this: "You see things and you say, why? But I dream things that never were, and I say, why not?" This questioning of why not is what that creates an exemplary researcher, and we wish all participants the success who are in the pursuit of researching. Hello, everyone. Thank you for joining us in the today's afternoon session. Let me introduce today's speaker, Dr. Anastasia. Dr. Anastasia Angelo Palau is an associate professor at the School of Computer Science and Engineering, University of Westminster since 2005, and a co-founder of Cognitive Computing Research Group, presently composed of 9 PhD students and 3 research associates. Prior joining with the University of Westminster, she held a position as research assistant in multimedia content processing for the European Culture 2000 FP7 program, and she has had 5 years industry experience in UK and Greece as image processing assistant and software developer. As an early career researcher, she has attracted over 250K pounds in research and consultancy funding from Dunhill Medical Trust and a few, and had published more than 50 peer-reviewed articles in top-tier conferences and journals, including 2 Springer book chapters, 9 Tier 1 journals, and namely Neural Networks, Neural Computing, Real-Time Image Processing, and a few more, and 30 flagship conferences like International Conference, European Conference, and Asian Conference on Computer Vision, an International Joint Conference on Neural Network. She has a total Sky citation of over 300 and a H-index of 10 from Google Scholar and 8 from Scopus. She has served and she is regularly invited by research councils such as EPSRC, UK, an Austrian agency for international cooperation in education and research, Austria, as evaluation panelist, grant proposal reviewer, and rapporteur to research proposals relevant to lifelong learning for intelligent systems and healthcare technologies. She has been an area editor and technical reviewer for Tier 1 scientific journals like Neural Networks, Neural Computing and Applications, and a few more, and has chaired various workshops and special sessions in the area of neural computing applied to vision, robotics, and crime detection and prevention. Her research interest includes computer vision, sign language recognition, multimedia systems, image processing, brain-computer interface systems, and multimodal human-computer interaction. She is also involved as a principal investigator and co-investigator in several research grants and consultancy projects like Automated Diagnostic Toolkit for Dementia and Dr. Snow and London Cholera Epidemic Games and Augmented Reality Storytelling and a few more. We welcome you, ma'am. It is indeed an honor for all of us to have you over here and hear from you. I now hand over the session to Dr. Angelo Palau.
Thank you so much for the introduction. Hello, everyone, and welcome to this session. I will try to share my PowerPoint presentations with you, and I will take you over what will be today's talk.
Jenkin, did you make her the co-host?
Is it possible? Because still I cannot share. Thank you.
At present, she's okay.
Make her the co-host or host so that she can share the screen.
Ma'am, I think we can share now.
Thank you.
Yes, it's visible.
Okay, so thank you again. Thank you everyone for joining this presentation. I would also like to thank Karunia University and particularly Professor Jude Hemant for inviting us to present our work. Today's presentation is going to be about machine learning, artificial intelligence in specific domains. One is in healthcare and the other one is in smart environments. Both of these domains has to do with case studies that we worked with research project. The first one actually is a finished research project and we already have the results and we have published papers for that. The second one, which is a collaboration with Karunia University and Jude Hemant, started 2 months ago, and we have until next year, end of next year, July 2020, to conclude the project, publish together, and actually have the results. Rida, who is going to be after me, he's the research associate that he's working on this project, and he has worked on the past project as well. So he's going to give you a sample of live coding and some live examples of the things that we have done so far. Today's presentation and those research projects, there is a collaboration between the University of Westminster, UCL, University College of London, and the project was funded from the Dunhill Medical Trust. The contributors to this project was Dr. Sing Liang, who is currently working again as a research associate with the Greenwich University, Dr. Epaminondas Kapetanios, who is working at the University of Westminster as well, Professor Ben Sewall from UCL, and Rida, who is going to carry on with the presentation. To give you an overview of today's presentation, I will start with some success stories of deep neural networks because there are a lot of things, there is a lot of discussion about deep neural networks. Neural networks are not new, they go back many, many years ago, but today with the facilities, with the many data that we have, with the actual computational resources, we can now put in place the deep neural networks and we can train our systems and we can have very, very good results. So we will start with a very, very small introduction, which maybe most of you are familiar with that, with the differences between what are the human brain networks, what are artificial neural networks, some basic concepts which they are used with the deep neural networks, like an activation function, what is backpropagation, and of course then we will have an introduction to convolution neural networks, which are the ones that we use mainly for imaging. And this is the networks that we have actually used for the 2 case studies. So the 2 case studies will be one, as I mentioned, about the Dunhill Medical Project, and it is automated diagnostic toolkit for dementia in aging deaf user of British Sign Language, BSL, while the second project is about intelligent transportation infrastructure for smart cities, you can put it like that. And we will conclude with some open research questions. So what is still very, very valid and where this AI is going and what are the next 10 years that we are looking for from this AI concept. So as you can see from the images that I have here, there are 2 cases, 2 scenarios, one which refers to traffic, and it has to do with object detection and recognition from a particular street where you have a number of cars and you classify the cars into different objects. So for example, you can have it as a car, but you can have it as a truck as well. Or you may be able to identify that this is a bus, or you might be able to identify this is a motorbike. So you can identify the different objects and categorize them based on where they belong to. You can also identify a person, you can identify a bicycle, you can identify some other things as well, like the traffic light. So this is an object detection scheme framework, which was developed, and it used the YOLO deep learning framework. Now, YOLO means you only look once. And actually, it's one of the state of the art in object detection systems for real-time processing. There are different versions. It started with version 1, I think currently is in version 4. And this type of deep learning actually frameworks has won all the most recent competition on image classification. And by now, it performs sometimes even better than humans at the tasks of recognizing objects. So YOLO is one such framework. On my right-hand side, there is another picture where, again, use deep neural networks, but it is now for caption generation. So instead only of recognizing the objects there, what you're trying to do is to put some semantics in the scene, to try and understand what is the content behind. So in this particular case, you actually have someone playing a guitar, and the system was able to put a caption that this man in black shirt is playing guitar. Similar, for example, for the worker on the right-hand side. All these things, they are coming from the image.net org, and they have been challenges where they won different competitions. Again, these are other successful stories where deep learning can be applied. Deep learning can also be applied in industrial application, in agricultural planning, in self-driving cars, the one that I have here, and also in gaming, which is very, very successful as well. In self-driving cars, there is a lot of fuss about self-driving cars. We are not there yet. It will take some time because it's a very complicated task. But a lot of companies, even big companies, but also startup companies, they're very, very interested in this technology, and they are investing quite a lot. And this takes into consideration computer vision methods plus some deep learning techniques and architectures. On the right-hand side, I have about gaming and artificial AI in gaming. And what you have here, you have a very well-known game, which is known as the Alpha game. This game actually originated in China over 3,000 years ago. So it's a board game, a very traditional board game, but now it has been a computerized game, and there is a lot of insight about reinforcement learning in order to be able to have very clever moves and try to win your opponent. The way that you play the game is that you have two players where they are using some stones. They can be black stones or white stones, and they take turns the way that they are placing them on the board. So the goal of the game is to surround and capture your opponent's stones, and strategically to try and create spaces of territory. So this is how you play the game, and the win is the one which has the highest number. So the same now, it has been used by using deep learning and reinforcement learning to try actually and beat your opponent. So these are some cases, some domains where we can see deep learning. But as Dr. Jude referred in his short presentation, there are other domains like the medical domain where deep learning can be used and can be very effective, especially if you have cancer detection or if you have a mole and you want to distinguish if it is a cancerous or not. So now, before carry on, I would like just to emphasize the differences between deep learning and traditional machine learning techniques. You can see there are two curves. The traditional machine learning technique, it goes up, but after a while, it kind of flattens, while the deep learning, the performance can improve and improve and improve. So the difference between the two is that in traditional machine learning, either you're using Bayesian techniques or any other type of techniques, you have the amount of training data, it increases the performance, but after a while, the shallow machine learning models will actually flatten. So even if you get more data, you cannot improve further the model. Something which is not the case with the deep learning. So in the deep learning, you continue to improve as long as the model is deep enough and you have a variety in your training data. So this is an advantage of deep learning compared to traditional machine learning. A second advantage is that if you look at the two pipelines where both of them, they have the input data, you get the output, and in the middle is where the pipeline is happening. For the deep learning, even if it's very complicated, the different layers that you put, however, what you have there, you learn specific functions where you connect the input data directly to the required output, making your model development much, much simpler. While in machine learning, what you have there, the pipeline can be very, very complicated. And most of the cases, in order to extract the features for your model training, you required an expert with great domain knowledge. So these are the two differences between the deep learning and the machine learning. So going now back to a small introduction about neural networks and where everything originated. Of course, it originated from the human brain, from the human neurons, and how actually we learn, how actually we make connection. And what I have here on the left-hand side is just a drawing representation of a biological neuron, while on the right-hand side here, you can see the mathematical model, the approximation of an artificial neural network. So what we can see in both cases is that in the biological neuron, what you have input signals, and those input signals, they are formed from the dendrites or dendrotes. Actually, this comes from the Greek word dendro, which means a tree. And there are these branches which they produces an output signal. So you can see there is a single output signal, which is called the axon. And the axon, later on, it branches and connects to other neurons. So you can see here, there, in the image below, these are the individual neurons. All these neurons, they have their own branches with the dendrites where they're communicating and they are connecting with the other neurons, but there is a single output all the time that goes from the neuron. So this is very, very in alliance with the artificial neural networks. However, the ANNs, they are much, much simpler in comparison to the biological neural networks, but they have some common similarities. And the fact is that you are having a number of inputs, and these inputs, they carry a signal, and this signal goes through an activation function, which is here, and it gives you a specific output. So this is the way that they have in common. And what we can see here is that this can be the nodes. So in that case, I may have two nodes as inputs. I may have a hidden layer. We will see later on what's that. So in that case, I may have three nodes on my hidden layer. And then, of course, this can give more outputs from the hidden layer. So a very, very simple representation and seeing the mathematical model of artificial neural networks is this diagram here, where what we actually have, we have a multivariate input. You can see the input can be x1, x2, up to xn. And this input, it can get the different inputs actually have associated weights. So there is an associated weight for the input one, there is an associated weight for the input n, and all this plus some bias, they are going to our actual node. And from what we can see there is that this is a very, very visual representation of linear regression, because y equals to x dot w plus b, this is actually in a vector form, the way that I represent it here, is a representation of linear regression. So linear regression generally in neural networks is a very, very attractive model because it's very simple to represent. And from this linear equation, what we have here, we combine a specific set of input values x, which are our input, the solution to which is going to be the predicted output value for the set of inputs. So y is the predicted output value, which comes from a set of inputs with a specific weight as well, plus a bias. So now, if we want to extend this graph to allow for a binary output, so something that can be classified as 0 and 1, or later on that I want to classify it as class 1 and class 2. So what we can do is we can now represent that as logistic regression. And all we have to do in order to have logistic regression, and in our cases, if we want to have a binary representation, it will be a binary logistic regression, we just need to add an activation function. So this activation function, as we can see in our example here, is a sigmoid function. Okay, so this sigmoid function is going to map and take the intervals, whatever are the values, to 0 and 1. So this will be the values that we are going to use for our binary outcome. However, we can also have multinomial logistic regression. So this was a binary logistic regression, but we may want to have more than 2 classes. Imagine that you have an example where you want to classify someone as vegetarian or non-vegetarian or vegan. So in this particular case, you have actually 3 classes that you want instead of 2. So this is going to be a multinomial logistic regression, and this activation function, sigmoid function, is not actually going to be the best for this type of classification, which means the way that you treat your data and the way that you represent your classes in the end as your output depends on the activation function that you are going to use. Again, this is another example with a different activation function. So here, instead of having a sigmoid, I'm using a perceptron. Similar with the sigmoid function, but now I have a steep step. So everything which is negative maps to 0, and everything which is positive maps to 1. So that's the perceptron activation function that we are having here in this particular example. And again, depends on the output, depends on what you want to classify. You can use different type of activation functions. This diagram just shows you the representation of the input layer. You can have your activation function here, where is happening all the calculations for your linear regression and then the logistic regression. And finally, you're getting the output, what you want to classify. This slide shows some very, very well-known activation functions. There are many more that can be used with deep neural networks and neural networks in general, but these are the most representative that we use with neural networks. The logistic, which was the sigmoid that we have just seen, can be used for logistic regression and can be used for binary logistic regression. You can have the perceptron, which is a step, as we just discussed, and 2 more activation functions, which they are very, very popular, and they're used a lot with the deep neural network, are the rectifier or ReLU, and again, the soft plus, which is a smooth version of the rectifier. Now, the rectified linear unit or ReLU is something that actually was motivated from biology. So it goes back, or the root comes from biology, and how actually we can use it in order, instead of taking a maximum like a step of 1, as we have with the logistic regression, what you have here with the rectifier is that everything which is negative actually maps to 0, but all the positive values of x, you get the maximum. So actually you are not bounding on the positive side as you're doing with the logistic here, or with the perceptron here. But as you see, it goes up, 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 so there is no bout on the positive sign. Similar with the soft plus, you see they have very, very similar representation. The only difference is that around the 0, you see there is a smoother version there of the rectifier. So in that particular case, that's why you define it with the logarithm of 1 plus e to the x. So that's the only difference between the two, that this is a smoother version of the rectifier. So now, what we have seen so far is that what we can do, we can have a number of multiple perceptrons, and if we stack one perceptron on top of the other and on top of the other, then we can actually having a deeper versions of that. So in this particular example, as you see there, what we can do is that we can feed the output of the previous nodes of the perceptron as inputs to the new nodes of the next perceptrons, and so forth and so forth. So instead of having only one perceptron, if this is the activation function that we are using, it might be the sigmoid, we can have as many as we like, and we can top up all the time, and the outputs of the first layer of this perceptron can be taken as the inputs to the second layer, and this can be taken again as inputs to the third layer, and so forth. And we start now to create deeper, fully connected neural networks by stacking perceptrons on top of one another. So we start introducing this concept of deep networks. So in a simplified version here, as you see, so what we have a model that we want to represent. And in this particular case, you have two classes, very, very simple. So you want to identify, okay, what is the best representation to separate the blue dots, let's say, from the red dots. And you can start with two linear models. So you have two linear models which they can best represent this class. So the first linear model, if you bring this line, it separates it this way, but you can see it's not perfect because you're getting as well red points here, which you don't want. Another linear model in that case is it separates the classes like that. So again, you have some falses there. So it's not the best way to represent the class. But if you combine those linear models with an activation function, then you can get this non-linearity. So now you can separate even better the classes between the blue and the red one. So in this particular case, what we have a single pair, as you see, of x1 and x2 points, which they are fed to the first model. The same input, x1 and x2, is fed to the second model as well, but we are having different weights for these particular inputs, and of course, an added bias. So instead of representing it like that, and on the right-hand side, you see exactly what is happening here, but now you're having your activation function, which is your sigmoid. So what we can do, instead of having two different representations of the input with the models, and going back again, is that we combine now. So the first input is connected to both models with the required weight, the weight that it was supposed for the first model and the second model. The second input, again, is connected to both models with their associated weights. And of course, the bias, again, is connected to both models. So in that case, we can diagrammatically simplify the previous case, and we can have in a single layer all our inputs. So this is the first layer where we are getting all our inputs. Then, in that example, we have a single hidden layer, which represents the linear models that we are using. And the final is the activation function, sorry, here, where actually by using the activation function, a sigmoid activation function, as in our example, we get the output. So the output is that this particular object, what is the probability of belonging to that class? So now it comes with a probability of 0.92 that this point belongs to class blue rather than to class red. So if we want now to see all the layers and how they stack together in a more mathematical term, what we have the input layer, we have the layer with our perceptron in that case. So our output Z is actually a linear combination of vectors of xw1 plus the bias. Careful, the bias here is a vector with as many components as the number of the nodes that we have in the layer, and the output, it comes actually from the activation function that we apply to the output of our layers that we used for the hidden layer. So the second case is now the second layer is going actually to take as input the result of the first layer. So whatever was the output of the first layer is going to be fed it as input to the second layer, plus of course some bias. So all the time we add a bias as well. And this can carry on for as many layers as you like. That's why now we also use this terminology of deep, because we can have hundreds of layers, hidden layers between the input and the output. And this is actually the representation of the many layers that you can stack one next to the other before actually using your final activation function to get your output. However, when we're dealing with data, real data, things are not as simple as class 1, class 2, or separated easily into separate classes. We may have much more advanced and complicated data sets like the one here, which is very difficult to easily separate it into different classes. So for these purposes, generally, we are looking for non-linearity. And this is the concept with the activation functions that we are using non-linear functions to be able to better represent our data set, which can be very, very complex. So in that case, you have a number of inputs here, you have a number of hidden layers. So in that case, I have 1, 2, 3, 4 hidden layers. Every hidden layer, it has a number of neurons, which are actually the nodes, and you can see based on how thick or not thick is the line represents the weighting. So how much weight, you can see that this node has higher weight to that particular node, while it has less weight to the rest of the nodes, and so forth. So in complicated cases like that, we may see that we may mix the activation functions and we may go for more advanced activation functions. So a final representation and diagrammatically representation of an artificial neural network is that you can have multiple inputs, x1, x2, you can have hidden layers, and you can have multiple outputs as well. So not only just a single output, as we have seen before, but you can have many outputs based on the problem at hand and what you want to classify. This concept and the way that you input the output of one layer as an input to the second layer is called also feed-forward neural networks, because there are no feedback loops to our network. So everything feed forwards to the next layer and to the next layer and so forth. Another term which is used a lot with artificial neural networks is backpropagation. So what is actually backpropagation and why it is very, very important? Generally, when we are using a network, we need to train our network. And when we are training a network, our goal is to get the desired output. So our desired output, we want to be the same with the actual output or as close as possible. So if you want and you have something to represent it with a specific value, you want the new value that you will get to be very, very close to the actual value. If this is not the case, then you will have to retrain again your network and you will have to backpropagate and try to see how actually you can minimize and you can fine-tune your weights. And how, by fine-tuning this weight, you can actually bring the error down. Now, the error is coming by an error function, which can be a very simple mean squared error function, and it measures what was your actual output and what is the desired output. And based on that, you can calculate how big is your error and how far your result deviates from the actual result. So the backpropagation goal is to minimize, which means brings as close to zero as possible, the value of all the training samples. So in other words, is to optimize the weights of the neural networks in order to be able to minimize the error. And this is what we see here in a very, very simple example, where what you have a pictorial representation of a number of inputs, input 1, input 2, it can be input 3, and so forth. You have the different nodes on the hidden layer. Careful, this is one hidden layer, but I have node 1 for the hidden layer, node 2 for the hidden layer, and so forth. And based on some random values for weights, what you want, and some bias, of course, what you want to calculate your actual output, you want to have 0.01 and 0.99. So the first time that you train the network, you want actually to achieve these values. But based on the weights that you have given, which they have been taken randomly, those values, you may see that you generate an error of 0.29. Okay, and this is not something that you really want. Maybe it's a big error around 0.3. So your task is actually to go back by using partial derivatives here of the total errors that you have and the weights. So actually you're trying to see with backpropagation, and that's the concept of backpropagation, how by changing the weights of the inputs to your hidden layer, and from the hidden layer, let's say, to the output, you can actually minimize this error. So by just going back again with the weights and changing the weights by using the gradient descent and this concept, then you may see that the next time that you train the error, for example, the error went back from 0.29 down to 0.28, which maybe doesn't seem much. However, if you repeat this process many, many times, sometimes it might be hundreds of times or even thousands of times, then you may see that the error can actually go down to 0.0003. And your output values that you're getting now from your network, they may be very, very close to the actual value. So you may have 0.015 for the first one, and for the next one you may have 0.96, which they're much closer to the 0.99, sorry, to the 0.99 and the 0.01 that you have here. So that's the whole idea behind backpropagation. Try to minimize and optimize the weights, and you are going back again and back again by taking the partial derivatives of the total error, which comes from your error function, and the different weights, in order to be able to fine-tune these weights and retrain again the network and get the actual results. So now that we have a better understanding of how traditional neural networks are working, the artificial neural networks, we will see the special case of this artificial neural network, which are the convolutional neural networks. And these are just examples of where convolution neural networks can be used. They can be used in face recognition, as you can see here, or it can be used in object detection, as we have seen at our second slide with the YOLO framework, which actually uses convolutional neural networks. And the whole concept behind the convolutional neural networks is now we use images, and images store information in pixels. So you can think about it as a two-dimensional grid. However, what is really important about the images and the pixels is that when we are trying to detect an object, in a particular image, we don't care if the image is black and white, or if it is colored, or if the object is somewhere in a different position in the image, and so forth. What we are looking is that we are looking for association. So we want to see the pixels that represent that object, how they correlate with another which they're close related. So actually we are trying to exploit relationships in order to have better understanding of the object and the surrounding environments. So CNNs work quite well with that by just looking at neighboring pixels, by trying to identify patterns which occur quite a lot in a particular image. And of course, CNNs can not only work for images, but they can also be used for text recognition, and they can also be used for sound as well. So these are the other two domains where we can find the convolution neural networks. So a simple architecture of a convolution neural networks, this particular architecture is coming from the MATLAB deep neural network, and it is a very popular image that is being used in the MATLAB framework. So what we have here, we have a number of input layers. So in that case, we have the car, we have the convolutional layers with the activation functions, the ReLU, we have some pooling. Okay, max pooling is the process that we are trying to downsize our images. So by using this pooling method, we reduce the size of the images, and then we push it to another convolutional layer, we downsampling again, we push it to another convolution, we downsampling, and so forth. And the final stage is our fully connected layers. And finally, we have the activation function, which is going to give us the classification for the output layer and the different type of classes. So if we want to make an analogy with the traditional neural networks, we will see that what they have in common is they have the input layer and they have the fully connected layer. So these are the two commonalities that we see between the two, because the fully connected layers that we have here in a convolution neural networks, what it is essentially is just a multi-layer perception parameterized by weights and bias values that make use of the softmax activation function. That's what it actually is, the fully connected layer here. So now, while we discussed about different activation functions with convolution neural networks, the most common function that is used as the output layer is the softmax. So it's not the soft plus. The soft plus is a smoother version of the ReLU. It is the softmax, and this is used in the last part of the network on the output because it can be used for multi-classification in logistic regression. So we have seen that a sigmoid activation function, it can also be used for binary logistic regression. But if we have a multi-classification with a number of different classes that we have, we use the softmax function. This is just an example of how images are represented. So you have them in a 2D grid, but whatever you have there, they're just a sequence of numbers. And this is an example of some digits, which comes from the MNIST dataset. Now, MNIST dataset is very, very famous because it has 100 digits, and it is actually a benchmark for image recognition. So it's a very well-known dataset if you have 100 digits and you want actually to see how much it can test with this particular dataset. It consists of approximately 70,000 images, and you see that the cells, which actually is the grid that you have, is 28 by 28, which they represent your digits. So in this particular example, and before feeding the image into our network, the best thing that we have to do with our training dataset is actually to rescale the image before feeding it, because we can save computational resources, since deep neural networks can be based on how many hidden layers you have and the training dataset that you have, it can be very computationally expensive. So what we have a number, we have the input layer, a number of hidden layers, and finally we have the output layer with the softmax, where in our case here, what we want to classify is a class of 10 between the digits 0 and 1. That's why we have 10 outputs, which is our 10 classes between the zeros 0 and 9. That's what we need to classify. Again, this is another example of convolutional neural networks as used in patterns. And different patterns. What you have here on the left-hand side, you have the digit 0. There may be some noise here as well. And you try to identify what are the best patterns that can be used when you're actually using the convolutional neural networks to better describe this particular image. So out of the 3 here, you can see that this pattern cannot be seen anywhere in the image, so it's not a good choice. However, both of them, they can be seen in the image. So for example, again, these are other patterns that can be used. And this area here actually match this pattern here. So this pattern and that pattern is actually from the particular images, which means, yes, they're good examples to represent and be part of the convolution when you're using the convolution neural networks. So the way now that convolution applies, we will see an example more with specific numbers, but you start always from left to right, and it's like scanning the image from the upper left corner to the bottom right corner. And you do that for every single pattern. In this case, we have another pattern that we want to represent. However, this is not a good representation if we want to classify the previous digit, which was 0. So it's very, very important to, based on what we want to classify, based on what is our training, what are the things that we want to be able to use the correct patterns and identifications. So going back to the convolution, what we see here is you have an image. In that case, you have the letter X, which it has numbers from -1 to 1. And on the left-hand side, what it is, this patch, this is a patch or a filter, is actually something that you found 4 times in your image. So these highlighted sections here, it show you that this is the exactly pattern that you identify in the image. So the next stage now is to do a 2D convolution between your filter and your image. So the way that you do the convolution is you scan the filter on top of the image and you multiply every pixel or every element of your filter with every element of your image, the particular patch of your image, and then you add them all together and you get, for example, the final value. So in that case, you multiply 1 times 1, so it will give you 1, -1 times -1, it will give you 1, and so forth, until you finish with the whole filter. But then you don't stop there. What you need now to do is that you actually take now the sum of all the products that you have come from the convolutional matrix and you divide it by the number of the elements in the patch. So actually you're just normalizing the sum by the area of the patch. And in this particular example, which represent this area of the image, we add all the values of the patch, which are here, we divide it by 9, and we find the relevant value, which is at 0.55. So you do that for the whole image. This was your selected pattern or filter. This is your image. This is the convolution symbol that you apply now, convolution. And what you end up with your convolutional matrix. So this convolution matrix actually gives you all the values and how much they are similar, the weights that you have there, it shows the similarity of that particular pixel to that particular pattern. So you see that 1, 1, 1, and 1, what actually means, it means that you had 4 equal patches in your image which match exactly the filter that you use. That's what it means there. Okay, that you had an actual match of 1 between your filter and between your image. So the next step, if you remember when we've seen the diagram of convolutional neural networks, we had convolution plus the activation function, the ReLU. So the ReLU is the activation function that we use in deep neural networks. And the whole concept behind, based on the diagram here, is that, as we said, all the negative numbers, they are mapped to 0, and all the numbers that they are positive, they actually get the maximum value. So based on these two matrix representation, you see everything which is negative, it maps to 0, while the maximum value of the pixel, you leave it as it is. So 5 remains 5, 4 remains 4, and so forth. So it's only the negative values that map to 0. Then it's the max pooling, which is again, now that we have done the first layer of convolution and the activation function, we max pool our layer, which means we need somehow to downsize the image because we save resources, we end up with smaller images, but we keep all the important information from the image. So we try not to lose information. So the max pooling actually in this particular part of the image is a new patch where it keeps the maximum value of the patch. So from the patch first, it was 4, from the second patch is 8, from the third part, 5, and from the last one is 6. So that's the whole idea of max pooling, downsampling your image. Make sure you have smaller images, but keep the important information from your image. So finally, this is the whole convolution and pooling process that you can have for your input. Depends what is your input. It might be a very simple input like that. It might be a more complicated input and so forth. You have the number of the layers. You are doing the convolution with the rectify. You're pulling it down sampling. You're doing the convolution, you down sampling and so forth until you reach the fully connected layers. And in the end, you use your output layer with a soft max. However, you see that as we are moving from one convolutional layer to the next convolutional layer, of course, we lose information. We are not losing exactly information, but we lose information that we can recognize. In that case, in the first, we have an image of a cat. We can still see the features of the cat. The second convolution layer, still we can see some of the edges of the cat. Then we move to a third layer, which now it's a little bit more difficult to recognize that this is a cat. And of course, as you are moving further down the convolution layers, then you get pixel information, which as human beings, it's very, very difficult to recognize. However, this information is very, very important because it gives you very, very low features that the system can use to train, such as edges, curvatures, and so on, and make the association. So all these layers, even if they are unrecognizable by us, are very, very important by the system. So this is just the final architecture of putting everything together and having a particular input through the first convolution and ReLU layer, second convolution ReLU layer, doing the pooling again, doing pooling, fully connected layer, and finally you have a softmax that you want to classify as an X or 0. Okay, so in that case you have two classes that you want to classify. So going back now to the approaches that we follow for deep learning, there are generally two ways that you can approach deep learning. Either you train a deep neural network from scratch, so you have the data set, it's your own data set, and you create the convolutional neural networks, you decide on the activation functions, and you use everything from scratch, which means you also need to label your data, you also need to denoise your data, you also need to do all the pre-processing to the data, which can be very laborious, and finally, you can classify the objects based on what you are looking. The second case, which actually is the most preferred among researchers, and this is actually what most researchers are using, is to use transfer learning. So actually you fine-tune an already trained model, like for example, something which comes from the YOLO, and you are already fine-tuning parts of this particular network, or from the VGG16. So there are different types of architectures that they have already been trained in millions of images that we can use, and we can actually retrain and modify the last layers. So this is the concept of transfer learning and what is more preferable among researchers. So some very well famous and pre-trained models are, all of you, I suppose, may be familiar with AlexNet, VGG16, 19, the GoogleNet, the ResNet, the SqueezeNet. So depends what you want to do, depends for which task you want to apply this particular neural network. There are already pre-trained models that can be used, and you can fine-tune these models and actually use it for the problem at hand that you have. So now, my second part of the presentation is going to be on the 2 case studies, and I will focus more on the first case study because we have results for this, we have our experiments, and we already published our outputs for this particular project. And as I mentioned, this is a funded project. It finished in March 2020. This is the identification code of the project, and it was a collaboration between our university, the University of Westminster, UCL, and it was funded by the Dunhill Medical Trust. So what we can see here is that we already know that the aging population is correlated with an increased prevalence of acquired cognitive impairments, such as dementia, because this is what we are trying to identify here, early stages of dementia. Although we know that there is no cure for dementia, however, it's very, very important to have a timely diagnosis, because this can help obtaining the necessary support and appropriate medication and all the care that you may have from care home people or from the nurses as soon as possible, rather than to leave it at a very late stage. So researchers are working to try and develop effective technological tools that can help doctors undertake early identifications of cognitive disorder. Now, you can imagine that in the case of BSL users, this is actually an extra challenge as well, because it's the communication, they're using a sign language and they are deaf. So there are many, many challenges, especially in the diagnostic process, since you don't have enough interpreters to assist when you're visiting, for example, a nurse in the NHS or anywhere else. And there are no well-appropriate questionnaires and cognitive tests in order to diagnose and help you with the early stages of dementia. So this extra challenge is something which is happening with the BSL signers, with the British Sign Language signers. Now, there are different types of signers as well. We focused on BSL because we used data from the BSL bank, which is from the UK population. You might be familiar with other sign languages, which is the ASL, the American Sign Language, but for this particular case, all our data, they are coming from the British population. So the aim of this project, of the automated diagnostic toolkit for dementia in aging population for BSL users, is actually to try and create a toolkit in order to be able to improve early screening for dementia among aging signers. And that was our ultimate goal for this particular project. So before carry on and see some of our methodology and what we used, I would like to give a very, very short introduction about what is BSL and what is the British Sign Languages. Generally, the sign languages are natural human languages, which they are created by the deaf communities, and they are unrelated to the spoken language. So they have their own language, we can put it like that. They make use of hand actions, face, and mouth movements and body movements. So the whole body, for example, used for the visual communication. And the BSL, the British, is for the British Sign Language, and there are different types of languages based on the regions that you are. So what you can see here, I'm going to show you a conversation video between two deaf people using the British Sign Language, which we used from the BSL corpus, the data set. And I will play it again. So you see, everything is activated. You have the mouse, you have the face, you have the hand actions. So all these movements, they are part of the conversation. On the left-hand side here, from the dictionary of the BSL, because there is a specific dictionary that is used in the BSL, you actually show the different areas where the BSL can happen. To give you an example, it's unlikely that the hands will be over your head. So it's not a common sign that you will find the BSL, or it's unlikely that you will have sign where both hands are extended. So all the signing is happening around this signing envelope, as we call it. And this is what we used in order to try and build our methodology of how actually we can differentiate people of early stages of dementia with people with their healthy signers. So it was an idea of trying to see if there is any difference in the sign space. And finally, on the last picture that you see there, all of the researchers
which we need to use to make the medical devices very smart. So we can start with information technologies like IoT, cloud computing, big data, artificial intelligence, along with the modern biotechnology. These are all the core parts of a smart healthcare system. So these technologies are widely used in all aspects of smart healthcare. So from the perspective of patients, they can use wearable devices to monitor their health at all times and seek their medical assistance through virtual assistants, as I said, and they can also use remote homes to implement their remote services. So from the perspective of doctors, if you see, we need variety of intelligent clinical decision support systems which are used for diagnosing
involved. We had, in order to get a better understanding of BSL, we actually attended some British Sign Language classes, which were specifically targeted for computer scientists by UCL deaf signers. So our speaker here, our teacher here, he was a deaf signer from USL, and we had some classes to better understand how BSL is working. So our methodology started first with the different data sets. We started with secondary data first, which means already data that we have from different projects and which are already available and free to use from the BSL corpus. Now, the BSL cognitive screen norming data, their video interviews with signers that they have actually found that some of them, they had mild cognitive tasks. So there may be some indication of early stages of dementia, and this is not available online for free, but you have to get access and permission from UCL. And then we actually used the BSL sign bank, where we use it as well just for very simple gestures when we tried first to test our methodology. In addition to that, we also had to do some new recordings, some video recordings. And we did that since some of the data that we used from the cognitive screening norming data, we had problems with the way that the camera was positioned. So while most of the cases, the interpreter and the signer were looking at the camera, we had a lot of cases where the camera was positioned from the side, so we didn't have clear picture of the signer, or we had other noise in the data, or for example, we had a lot of pauses between the signing. So for these purposes, we actually had to get and create a new data set. For this new data set, we collected interviews with 40 old signers, and it was a mixture of healthy signers and people with mild cognitive impairment or early stages of dementia. And the collection was supervised by a psychologist from UCL, who is a deaf native speaker, and what we have actually achieved so far. So in a more less academic, but more intuitive way, so this can be understood by these people. So part of the methodology is to use a feature extraction model. As I mentioned before, we already identified that clinical observations, they have already suggested that there may be differences in the envelope of sign space and movements of face between signers with dementia and healthy signers. So based on this hypothesis, we try to build the whole model and try to identify how we get our features, how we extract these features, and then how we feed these features to the network. So for these purposes, we used two different extraction methods. One, which goes to traditional image processing methods by using skin color segmentation. And we use different types of color spaces, HSV, LAP, Y, CRCB, and so forth. While the second approach goes to deep neural networks, and we use the OpenPose skeleton model, which works with convolution, two-branch multi-stage convolution neural networks, and you also get a prediction of a set of 2D vector fields, which they encode the location and the orientation of the limbs over the image domain as part of the affinity fields. So again, these are the two different approaches. They have their pros and cons, the way that you set up, how computation expensive they are, and the facial analysis model, where we wanted to extract how active or non-active is a face. So this was the approach that we followed. We also added later on another stage, which is an elbow distribution. So having now the gesture, having now the tracking of the sign space of our gestures, we try to identify how much movement do we have around the elbows, which is again another indication of a limited sign space or a bigger sign space, which is a differentiation between a mild cognitive impairment signer and a healthy signer. So the two models, the first model, which is a color filtering model, can be seen here. So what you have the following pipeline. So you get the number of frames, you're doing a face detection, which is used by using the HAR cascade classifier, very well-known classifiers for the facial expression analysis. Then you convert your video frames from RGB data to the different type of color spaces. You filter out the skin color, and of course you can get some noise as well, and you try to apply some morphological effects in order to connect any gaps that you have or eliminate any noise that you don't want, so actually to denoise your image. Then you are looking for contours of both hands by first sorting the contours by the area, get the larger two contours, get the two hands out. Then you are secondly sorting contours by position, so get hands from left to right, and finally draw a convex hole, as you can see here, around the normal contours that you have identified for your hand. So tracking now hand movement trajectory based on the contour mass centroid. So from here to there, you see what is the process with the color filtering. And I have a video which actually demonstrates the whole process by using the color filtering. In this example, what you have seen in real time this process. In order to use the method, we used Python 3.65, we used OpenCV, and we actually applied to both CPU and GPU architecture, which was much, much faster. And in that particular video, what you see three different signs. I will play it from the beginning. So there are three signs that differ in location in signing space, and one is the cloud, the second one is the picture, so this is the cloud, the second is a picture, which is like a rectangle frame, and the last one is the sailor. So it's a third sign which shows you the sailor. So you have three different types of gestures there that can happen at different areas of your sign space. Now we have, again, there are some videos where you can see the extraction of the trajectories. We have it on 3D and also on 2D tracking trajectory. So the 2D shows you for the left hand and for the right hand, and it actually tracks in time as well. So another thing that we were very interesting is how this trajectory, how the sign actually performs after a number of frames and during the time. Because if we have a sudden drop, for example, or if there are too many poses, this can be an indication of stages of dementia or not. So time, which we actually took it in milliseconds, was very, very important in the hand movement, and it was part of our model that we calculated. For the different types of color filtering models, we used different thresholds, and you can see here the different thresholds that we used for the RGB to HSV, RGB to YCB, and RGB to CA-LEP. So these are the thresholds that we used. And in this image, we actually tried to identify the accuracy of our model. So we wanted to see how many false negative we have, how many false positive we have, what is the best actual color model that can be used, and always comparing it with the ground truth. So this is what you have. This is the ground truth that you get only for the hands. Based on this slide here, we wanted to check what is false negatives and false positives. So this was used by using specific segmentation matrix. Image segmentation uses two very well-known metrics in order to segment the skin color and try to actually map it. What is the difference between what you get with the ground truth? So the two segmentation matrix that we applied is the Sorenson dice coefficient, which is this one, and it is the Jacquard similarity. And as I said, both of them are the state of the art when you are performing standard segmentation performance metric. The Jacquard similarity coefficient, which is this one, what it actually measures, it measures the number of pixels which they are common to both the ground truth and the segmented regions, and divides that by the total number of pixels present across both regions. Okay, so that's what the Jacquard is measuring, and similar what the dice. Based on that, we get some quantitative results of the previous matrix, where we have the different signing images, we have the different type of color models, and then we compare the dice and the Jacquard for the color models. So based on that, we have seen that generally, both models, HSV and CI-LAB, they're much, much better than the YCR and CB. And either one or the two can be equally used if you want to extract and use it for a sign trajectory. So the first method had to do with traditional image processing techniques, and we used color filtering, we used classifiers, hard classifiers for the face extraction, we used morphological operations, we used contour, and we used all these traditional image processing techniques to classify and be able to get the gesture. The second method is based on the open pose method. So now it's based on the deep learning, which was developed by the Carnegie Mellon University. And what you have here, you can actually get a skeleton in real time for the different parts of the body. So you can have it for the face, you can have it for the hands, you can have it for the legs, and so forth. Now, for our hand tracking model, generally open pose consists of 18 key points, but since actually we only use the upper part of the signer, so we are not interested about the legs or how they perform. For our purposes, we only use the 14 upper body part of the skeleton. So you can think about it, if you cut it here, we left out those 4 points because they were not important for our case study. And again, we implemented that both on CPU and GPU. CPU, it was quite slow, and we only focused on the GPU. So we tried first with the CPU, but it was it was lacking. So we decided to go to the 2 NVIDIA cards that we had and do all the computation on the GPU in order to speed up our results. And this is an example of the open pose tracking hand model that we used for one of the signers. And what you see here, you see how many frames per second we are getting, which is quite good. Around 14, 15 is quite good as a speed. So as you can see, I stopped the video there because it was very similar to what you have seen with the diagrams. What we get in real time the extraction of the gestures in the sign trajectory. And then we get that both in 2D and in 3D representation by taking into consideration the time and where the different peaks are. These are the examples of what we got when we compared mild cognitive impairment signers versus healthy signers. So the first picture here, the top, it shows what is a sign trajectory after a number of frames for a signer which has early stages of dementia, and how the sign trajectory of a healthy signer looks like. So there are very, very clear differences here. For example, the differences are between the sign envelope, how much bigger is the sign envelope for the healthy signer, and how much more narrow is the sign envelope of the mild cognitive impairment. Also, another difference we can see is that for MSI signers, we can see that the trajectory resembles more like a straight line. So yes, you have some ups and downs, but normally it looks like a straight line, rather than the trajectory of a healthy signer, where you can see a very, very vivid trajectory with up and down, some peaks. So it's much more active compared to the MCI. Now, since we decided that we are going for 2 comparative methods, either a traditional image processing method, which is a traditional machine learning method, or a deep neural network method, we have already seen their differences, the setup of the environment and what we get. We had now somehow to measure the accuracy with a ground truth data. So to get our ground truth data, we used actually a magnetic positional tracker, a Polhemus, which gives you a static accuracy of 0.08, and it has a resolution of 0.0005 centimeter of the range. And we had the electrodes where they were attached, for example, to the signers here. So you can see there are 2 electrodes, and in that particular case, we are actually just do a very, very simple sign like the number 3, and we try to see how much is going, which of the 2 methods is going to better resemble this particular actually sign. So in this case, and in these diagrams here, what you have the input of the sign depth from a web camera. We take the skeleton tracking model and we take the color model and we try to compare it with the tracker. So the green line represents the sign that we get from the tracker, while the straight line, the purple line represents here what we actually get as a sign from the color model. And on the right-hand side, we have exactly the same. So this is the tracker, which is our ground truth data. And this is the skeleton. So actually the same sign, but how this sign is being represented by the skeleton. So by just looking at the two, you can easily identify that already the skeleton gives a much better resemblance, or it's very, very close to the ground truth data. While the color model, there are a lot of information that we are missing in the tracking process of the sign gesture. So based on these two, we actually decided that there are pros, there are cons for the two methods. Maybe one is much more computationally expensive, which is the open pose, but it is much more robust. You don't need to do so much pre-processing as you require with the color filtering model, because in the color filtering model, you have somehow to have a very set up environment where you don't have colors which they are very, very similar to the skin color. So it will be a little bit unrealistic in a real environment. And also, based on the comparisons with the ground truth, we are missing a lot of information. So after we decided that we are going to go along with the open pose, so this is actually our model for the sign trajectory, then we build our pipeline of the neural network, what we want to do and what is the classification that we want to have. So what you see here are all the different features that we are applying to the CNN model. Our convolutional neural network model that we used for this is the VGG16 and the ResNet. So actually we applied transfer learning. We use already pre-trained models, but we modified the input layer and we modified the output layer and the last fully connected layer in order actually to get the classification that we want. So instead of having objects like cars, like trucks and different things, we wanted to be able to classify it as healthy and likely MCI or early stages of dementia. So the pipeline consists of three different types of features. One is the open pose skeleton, which gives the sign trajectory and the features extracted per signer. The second part of our model is the facial motion, so the different features and the distances that we get from the different signers and how active or non-active is the face. And the last part is the elbow distribution, which, as you can see around the signer space, which is this one, we have put some elbow distribution in order to see how we deviate and how big or small is the sign space. Our actual methodology, our actual model so far is taking only input from the first features. So the implementation of our model and our accuracy, our prediction is based on the first. That's why we have it current work. We want to carry on, and in the next year, we have already done a lot of work with the facial and the open pose. We have all the features here, so the only thing now is just to feed those extra features onto the network and have two more models and improve a bit more our accuracy of the model. So the facial analysis model is based on the DLIP library, and it has to do with a number of facial landmarks. So these landmarks, they are coming from this detector. And in order to be able to analyze the facial expression, the face detector uses the very, very classical histogram of oriented gradients, which you may know it as HOG. And these are combined with a linear classifier, an image pyramid, and a sliding window detection scheme. So all these are used in order to detect the different landmarks of the face. So for this one, we use the pre-trained facial landmark detector, where it has 68 XY coordinates. So you can see you have in total of 68 landmarks, which they coordinate to the facial features. And we tried, based on this facial model, to calculate the different distances. So this particular example, the video shows again in real time how we extract the facial features and how we actually calculate the distances between the different parts.
exams, huh? Exam.
Okay, so what you actually seen from the two videos, there may be some, I will play it, of the frame rates here. So we have a more real-time frame rate for this signer, while for this one is a little bit slower, but this has nothing to do with the sign space. So you can see the sign space, it's much more reduced, but there is a little bit of lag there of the frame rates per second that we were getting. That's the only difference. However, based on the results that we get there, what we were actually doing, we were calculating the average Euclidean distance differences between the nose and the right brow as D1, the nose and the left brow as D2, and finally the differences between the upper and the lower lips as D3. So we did that for a healthy signer, and we did that for an indication of a signer which we know in the second part of the video has early stages of dementia, because we know that from the cognitive test that we get. And we calculated that, and we found that the distances, the values, they're much less, for example, for people with MCI compared to the healthy signers. So there is less active facial motion expression for people with early stages of dementia. And again, this is putting now everything all together. This is a healthy individual, an MCI individual. This is a healthy individual. We have their sign trajectories here. There are the sign trajectories for a healthy individual there. And these are also the distances that you see for an MCI and a healthy individual. And especially you can see the upper and the lower lip, the D3 distance, it makes a big difference because we compare that with all our signers, healthy and non-healthy. And we found that especially how much they are using their mouth movements, it's a very, very good indication of non-facial expression movements around the mouth. So the next model, which has to do with other features that we want to extract, and you are going to see some demo of that from Rita, has to do with the elbow distribution. So going back to the trajectory where, as you can see here, you have a sign trajectory. So this can be very, very cloudy, your sign trajectory, or it can look something like that. Depends how many times you left in order to get your sign space, how many times you run the video. What we have here, we created a elbow distribution model. So we have a midpoint where in that case, we are taking the belly button of the actual presenter, the signer, and then we are getting a virtual coordinate system where we are calculating again the Euclidean distance between the virtual coordinate system and how this point is moving in relation to the midpoint, which is our reference point. And what you see here, for example, those dots, it actually shows you the distance based on the relative coordinate system and the reference point as well. Now, based on that, we were able, and you have here the examples of the healthy signer and the examples of a signer with an early stage of dementia. And what we see, we are getting the histograms and the probability in order to be able to compare the two based on what we get from the elbow distribution. And clearly you can see that we have a much smoother, much more Gaussian distribution, normal distribution for the healthy signer, while for the signer with early stages of dementia with mild cognitive impairment, you can see it is skewed a little bit, the distribution, it is spiky, so it's not a normal distribution. Also, the standard deviation is another indicator. So we have very, very small standard deviation between the signing space, while here we have much larger standard deviation. So it means that we have a bigger sign space, and the way that their elbows are moving inside or outside, for example, they are much more active compared to the MCI signer. So these were the different feature models that we have. We have the sign trajectory space, we have the facial expression model space, and we have the elbow distribution space. So the next part is to use now a pre-trained model. We tried the ResNet 50 and the VGG16 and tried to fit these features. As I said, our current work so far is that we are feeding only the sign envelope space, the trajectories of the sign, not the facial, not the elbow distribution yet. This is the next work that we are doing, that we want to carry on. So we are doing that, we are using those pre-trained models, and of course, we adapt the last layer of our pre-trained models in order to be able to classify our two classes. So in our case, our two classes are healthy and mild cognitive impairments. So this is an example of how the architecture of the two CNNs that we use, the ResNet and the VGG60. So we are freezing, as you see here, all these layers. And the only thing is that we are retraining the last layer, the last fully connected layer with the ReLU. We are also introducing a dropout layer because we don't want to overfit our model, and this is very, very important. And finally, we retrain the softmax, which is the last layer, in order to be able to classify it as healthy or MCI. And we do exactly the same with the ResNet architecture. The only thing here is that we are actually adjusting the last train layer with the softmax. So based on that, what we get is these are the results that we have used for our validations, and they have been used in the training process. We used 162 segmented cases. We trained 0.8, we validated 0.2, which is normal, 80% for training, 20% for that validation. We also had 6 cases, 6 separate cases that we tested as well, and we segmented into 14 with 1 MCI and 5 healthy signers. And again, these were not part of our validation training set, but they were kept separate. And based on that, based on the different networks that we used, we calculated the accuracy of the model and the ROC curves and the confusion matrices. And we already found that both for the 40 participants and the 6 participants which we kept as validations, and we didn't know at all what were the scoring. So we only learned after our network identified that 5 are healthy and 1 are MCI. So for these participants, we as researchers, we already had the cognitive test data. But for the last participants, it was only UCL that knew about the results. So actually, they only shared how many of these pool of participants are healthy and how many they are with mild cognitive impairments after we tested the network. So we can see that the performance is 87.87, which is quite good for this very, very small data set, because we used a very, very small data set. We didn't have millions of videos or images in order to work on and train our data. And similar, the accuracy and the ROC for the 6 participants is very good as well. So based on that, we already found that, okay, the VGG16 performs better than the ResNet, the way that it performs on the network and the way that we actually stop the network, where we stopped it after 15 epochs, okay, in order not to overfit, but be able to train as well. This is the confusion matrices for the VGG16, and these are the 2 confusion matrices for the ResNet model. Again, these are the ROC curves that we got for both models just to check the accuracy and how good they are with what we want to represent. And we can easily, clearly see that VGG outperforms the ResNet. And these are the cases that we get for the 6 participants. So now that we identify from those 2 pre-trained models, deep learning models, which one is best, we only use the VGG16 for the last 6 cases with 5 healthy individuals and 1 MCI. You can see that we had some false positives as well, which is in this case here, in that case here, where it has been misclassified. However, overall, the system managed to classify and predict that based on the different subcases, this is a healthy signer. And the ground truth, which was data that were hauled from UCL, confirmed that yes, this is a healthy individual. So even if we had in the subcases some misclassification, overall the system gave, in this particular 6 cases, gave 100% accuracy of who is healthy and who is, for example, with mild cognitive impairments. And finally, we wanted to actually justify our case of the deep neural networks, and we tested with some other state-of-the-art networks. So one is a shallow logistic regression, and the other one is a support vector machine. Because since we don't have such a huge data set, maybe it's not why we complicate and we use such architectures. You can see that for such a very small data set, still VGG16 outperforms the other 2, but it is marginally for the test accuracy. So it is 87.8 here, while for the logistic regression is 86.15, and for the support vector machine is 73.8. So yes, for the 2, there is a marginal improvement. However, the goal of this project is that we aspire to train and apply our model with increasingly larger numbers of data available from different signers. This was a pilot study. It was with specific data set from 40 individuals. But of course, if this is escalate with thousands of cases or hundreds of thousands of cases, then this model is much more capable of predicting differences between MCI and healthy individuals. So the future work that we have, which we already have the features extracted, is the second model, which are the facial features, which we have already extracted them now. The only thing is that we need to add them into the network. And the elbow distribution model, which is, again, we have extracted the distribution and how it varies between the reference model, between the reference coordinate system and what we use as the origin of the belly button, and how this deviate, and we need again to add that as a third model to our network. So to conclude, that was the first case study, and we have published already our results to academia. We now need to go back and try to present our results in a more intuitive way to the community, to the deaf community, and try to tell them what we found out through this pilot study. And of course, what is the next stage, how we can escalate that and how we can make it for bigger cases with more data sets. The second case study, which is very, very brief because it just started, is about intelligent transportation infrastructure for smart cities. And one of these cities that we want to use is actually the India city, and it was a collaboration, it is a collaboration with Dr. Jude Hemant and Dr. Anitha. And what we are trying to do is we want to find an innovative solution of a traffic management model which will take into consideration different important factors. For example, quality of life, environmental condition, traffic capabilities, and try to make recommendations to the public. So it is a twofold aim project. The first has to do with monitor road behavior for example, different types of cars, what type of car it is, if those cars, they violate specific time road restrictions, or they violate specific lanes that are in the road and they're only permitted by special vehicles or emergency vehicles and not by the normal trucks. So that's one thing which, again, we will use a deep learning architecture similar to YOLO to be able to identify that. While the second part is creating a management model where we gather the data from the streets by different sensors. We can use the cameras, we can use microphones, we can use other sensors which maybe measure, for example, pollution, and try and make recommendations to the public. What are the areas that they can go, or what are the areas of the city that they should bypass because the pollution probably is too high there, or it is too noisy, and of course try and suggest some alternative routes that can be followed with taking the traveling time into accommodation. So for example, we cannot suggest something that takes 2 hours over the normal time. So all these are factors that we will have to consider. So finally, all these are really nice with deep neural networks, with AI, which is there. AI is now in our lives. It makes recommendations. We can have it in many domains. We can have it in chatbots, for example, where you have a conversational system with your GP. You can have it some recommendations for hiring mortgages. You can have it in driverless cars. You can have it in robotics. There are a lot of different domains now that they use AI, and actually we are surrounded of AI. However, what is the main problem of AI and why this is so complicated? What is a black box there that still we cannot understand in these AI systems? And the main problem is that AI systems cannot explain themselves. They use complex algorithms at their core, and we don't get any explanation of what is happening there. And this is very, very important, especially in the medical domain when you're getting information. So the last slide that I would like to close with is with a...
If your doctor suggested major surgery and instead of providing an adequate explanation, they told you, it's too complicated for you to understand, you would probably want a second opinion from someone who can explain their rationale. That's where we are with AI today. Their accuracy keeps improving, and they are being developed everywhere to diagnose illnesses, to evaluate credit applications, and even to drive our cars. But many of today's AI systems can't explain their reasoning. Join us as we sit down with Daniel S. Weld and Gagan Bansal from the Paul G. Allen School of Computer Science and Engineering at the University of Washington in Seattle to discuss the challenge of crafting intelligible intelligence.
Intelligibility is the ability of an AI system to explain its decisions. These systems often make decisions for us, and in all these situations, we want them to give us a rationale for the decision that they make.
AI systems don't always give the right answer, and so it's extremely important that they be intelligible so that people can better trust them.
We need to understand why are they doing what they're doing, and where are they making mistakes, and why are they making those mistakes. And then we can begin to improve them or debug them.
We argue that people should be using intelligible models if they can. But in many situations, for example, computer vision problems and natural language processing, you just don't get adequate performance with intelligible models. So we're forced to use unscrutable models, and that raises the question about how can we understand what they're doing.
What we want the system to give is an explanation tailored to that particular instance or that situation, and that's where local explanations come in.
Methods such as generating approximate explanations and changing the explanatory vocabulary can increase the intelligibility of inscrutable models and help to figure out which details to omit from an explanation.
When you ask for an explanation, for example, why did the computer think that it was a bald eagle in the picture, you don't want the system to come back and say pixel number 532 has a grayscale value of 17. You want it to use higher level features like the color of the beak or the color of the head. So we need to do a translation from the actual features the AI system is using into semantic semantically meaningful features that a person can understand.
Research from psychology tells us that explanations are best thought of as a conversation. When I ask you for an explanation for a decision you make, it's very unlikely that you will be able to explain everything. As a result, I'm going to have follow-up questions for you.
An AI system that explains itself needs to know how to answer those follow-up questions interactively. One challenge with generating explanations is that all explanations are contrastive. The explanation is made with respect to a specific alternative called the foil. The foil is usually not mentioned explicitly by the person asking the question, and so the AI system has to induce what the foil is.
In this paper, our goal was to make a case for intelligibility and to summarize the state of the art in explainable AI.
Our goal is to build AI systems that can explain themselves and, as a result, be better teammates for working with people.
Find out more in The Challenge of Crafting Intelligible Intelligence, a review article in the June 2019 Communications of the ACM.
Okay, I would like to stop here. I have put all the references of our work, of our publications, and the references to this talk. We also have, you can find here actually the website of the project, which is updated regularly with more videos and more publications and more news and events of what is actually we are doing as a team. You can also find here the GitHub where we have, I will click on that, where you can actually see the code of the different methods that we have developed on the GitHub. For example, the hand movement trajectory, where you can see here we have uploaded everything to the GitHub. And another one is about the toolkit for dementia. Again, we have uploaded here our results and the different citations. So I will stop here, and I'm very, very happy. Thanks for listening. I will stop sharing my screen, and I'm happy to take any questions that you may have.
Thank you, Dr. Anastasia, for your presentation. It was very informative, and it was a heavy punch presentation in terms of applications. Thank you very much. I think we'll have Reda's a demo for another 5 minutes or 10 minutes. Then we will go into the question and answer session where the participants can interact with the speakers. Just Reda, I would like request you to finish within 5 to 10 minutes. Thank you. Jenkins?
Yes, sir. I'm giving it. You can share. I would like to introduce a few before he starts with the presentation. Reda Al-Battat is an BA, Bachelor of Engineering Software Engineering graduate from the University of Westminster, and currently is an MSc Artificial Intelligence is doing Artificial Intelligence at Queen Mary University. And as far as he is a research associate at the University of Westminster, working on an intelligent transport infrastructure project using AI-based methods. He has also helped a few PhD students on projects involved with deep learning and computer vision to analyze sign languages in terms of sign trajectory, sign speed, together with the facial expressions of deaf individuals. Thank you, Reda, for accepting our invitation and joining us to show us your work.
Okay, yeah, thank you for having us, and thanks for the introduction. I'm gonna start by sharing my screen now. Okay, everyone should be able to see the screen now.
Yes.
So in this last segment of our part, I just want to quickly go over some of the applications of deep learning. So we're going to be looking at the autonomous RC car, so an RC car driving by itself on a road system. We're also going to have a look at a simple traffic sign detector, and also look at a live demo of what Dr. Natasha talked about extracting the elbow motion. just briefly showing the general pipeline of how you would apply deep learning to different projects. So I'm going to be using a Jupyter Notebook, which is just an environment which allows you to run cells, if you're not familiar with that, with Python and TensorFlow and Keras. So first, I'm going to look at the autonomous RC car project. So as with all data science project, it all starts with the data. And in this case, we collect, in this project, we do the data collection ourselves. So how it works here is for every frame. So this is what, if the car is in this position in the road, this is the frame it sees, and so the image is the input and the label is the key pressed. So the key press for that frame will be either left, forward, or right. So we record that for every frame, and we record all of this data for going forward and back, for the left turns and the right turns. So we cover all the actions of the car for all of the states. Now, once we've collected the data, we need to load and visualize it and just observe some key aspects of the data. So here we can see, so this is a bar chart of showing how many frames we have for the forward direction, for the left direction and right direction. We can see there's an imbalance. Usually you don't want an imbalance in data, but in this case, because the road consists more of forward road rather than turns, it makes sense to have a large number of forward frames. So generally you want to have balanced data, but in this case, we want to have more forward frames for that reason. And here we also double check, we split to training and validation set. We also check that this is, again, the same applies for the both sets. And to help with the generalization, we apply some data augmentation, for example, zooming. Here the image is zoomed, we do the panning and alter the brightness randomly, and then flipping as well, just increasing our data set and making our model more generalizable. And then we perform random augmentation combinations of these. So each combination, each augmentation has a 50% chance of happening, and we can test it here. So for example, all these here. So here we have panning and darkness augmentation, which will make it just harder and more generalizable for the model. And then we do data cleaning and pre-processing, like cropping it. For example, we're not interested in the whole frame. We just want the road. So we crop it. We change it to a much better color space. In this case, we use YUV, which almost acts like segmentation, which is great. And next, we can see some examples of the data augmentation and pre-processing at the same time. And then here we create the model, which is a convolution neural network. This is how, just following your architecture, this is how you implement it. If you're a researcher and all that, and you hear all these buzzwords about neural networks and all of that, this is how it's built. You just choose, you add your layers and you choose how many neurons and you stack them the way you have your architecture. And this is, we have, so for this model, for example, we have about 350,000 trainable parameters. Now we go on to train the model. We get accuracy of around 80, and same with the loss. And I have a, so I'm rushing through this because initially it was planned for longer, but it should be fine. So here is a demo of the autonomous car in action, quick demo. So here is going right in the right turns. Here demonstrating the right, that was the forward. And same for the left here. And that's that project. So another quickly another project, we want to create a traffic road sign detector. So we want to detect where the sign is and classify what the sign is. So our dataset is a German dataset of 43 different science labels, and I did want to use an Indian dataset, but I unfortunately couldn't find any. So we have settled for the German dataset. And here again, you will see similar pipeline. We load the data, we analyze a view what kind of data we have. So for example, here we have 43 different signs or classes. And here, so we have the speed limits, stop signs, all of these. And then here we have a look at our classes. And one thing to note, these are patches of the signs. They're not part of a full frame. So it's only a classification problem. And we'll see how the detection will happen afterwards. And again, here we see, we count how many for each class we have signs. So for example, for the 0 class, which is the speed limit of 20, we have considerably less than the 30 speed limit. This ideally you want, normally you want the same like distribution of the classes, we won't have equal. But in this case, because 30 signs are much more common than 20, you want to actually have more, or is fine if you have a larger amount of data for the 30 signs. So you gotta look at it that way. And this is just some pre-processing on the image. We also apply some data augmentation, height, shift, and zoom, shear, and rotation. And here is demos of the data augmentations. And we can see we have this 34,000 training data, validation we have 4,000 and 12,000 for the test. And here again, we create a simple convolutional neural network with a softmax activation because it's a classification problem, as Dr. Natasha mentioned about the softmax. And then here we train the model, and here we see that we get very high accuracy, or about 98 training accuracy and validation. So, and if we evaluate on a test set, we get overall 97% accuracy, which is very decent. And then here we demo it. So the top on the title here, the ground truth and the prediction is keep right, and we can see even a hard ones like this one classified it correctly. And here's a demo of that in action. So you can see also is able to take multiple signs at the same time while maintaining 30 FPS in real time. And that's that one. And lastly, I want to cover the elbow tracking, which Natasha talked about and explained how it happens. So sometimes we can't use the raw data for deep learning. We need it's very complex, or it gets very, very complex really fast if you're going to use video data for deep learning. This is very hard. For example, this is an example of our data set, and we want to detect if a person is healthy or has dementia. And you can see from just the video, if we feed the video into the deep neural network, it's very hard for it to distinguish. So this is where we need extract features. So as Dr. Natasha talked about, one of the features we had is the sign envelope. So keeping track of the arms of it, and this is a trajectory over time. So that's one of the features. But the more features, the better. And we talked about how we can also use the elbow, because there was an observation made where healthy individuals, they sign more away from their body, where unhealthy they do their sign close to the body. So if we somehow can extract that elbow motion, then we can have that as an additional feature for the network. And the way we did this is create like a virtual origin, which is the mean distance from the midpoint of the body to the elbow. So first we will run the algorithm to find the mean distance, and then run it again to get the distance from the mean to the elbow. And that gives us a distribution. So first we can visualize this here just to get a better idea. So we can see here, this is the midpoint here, and this is the right elbow buffer, and we can see it's tracked over the frames, and we keep track of all these until the end of the video, and then we get this histogram here, which is going to be a really good representation of the elbow movement, and we can use as an additional feature to feed into the model. And that's all I had to show. And thank you for that.
Thank you, Reda. That is indeed very interesting, and I hope your codes, Python codes, will be useful for the researchers to take further or do some applications related to what you have shown now. Thank you very much. And now we will go into the question answer session. Participants, if you want to interact with the speakers, you can directly come to the Zoom, or you can type in the chat box. Dr. Anushya will be the moderator for this question answer session. Anushya?
Yes, sir. So participants, if you have any questions, please post them in the chat window. I will ask the questions, or you can directly come on and ask the questions to the speakers. So any questions from the participants? We have one question. What is the need of bias?
Dr. Anastasia?
Yeah, exactly. I've just seen the question. So you need to add to your data some kind of a bias, because in real life, you don't always have what you should expect to have. So as in an image, you have different types of noises, which they're part of your training set. Exactly, you need to add this bias as well to your training set. And you need to make sure that whatever is your bias, either it comes from the medical domain or it comes from any other domain, you try to explain it and justify it as much as you can in order to eliminate it at the end. So that's the concept of the bias, is something that you already have happening in your training set, and you include it already in your model, because you will never have a perfect model.
So just to add to that, actually, if you think about a linear regression model, a line equation, if you don't have the bias, you can only change the slope of the line. You can't move the line. So if you add the bias, then you can actually move the curve rather than just changing it, being to change the slope of the curve. So that's one way to look at it as well.
There's another question. Please explain in a ReLU function, when you have binary classification, why does 0 have no gradient but 1 has a slope? Is it because of the activation function that is applied?
The activation function, I mean, the specific activation function, which is the ReLU, as you see, it tries and maps all the negatives values to 0, and actually it keeps the maximum value of the X. So what you have there, you don't have a maximum value of 1, but you can get the maximum value of whatever is your input value is given there. So it's only the sigmoid where actually you have the 0 and the 1 that you map. The ReLU, it maps everything to 0, so you get rid of any negative numbers that you have, and it still keeps, especially in the images where you don't need to have the negative numbers, since whatever is your model, you want to map it either to 0 to 1, or you want to map it to the color space from 0 to 255, so you want to get rid of any negative values, but you still keep whatever is your positive value, the maximum of your positive value.
The next question is, how could we choose the value of bias?
Rita, would you like to say how you chose in your experiments, how you chose the value of the bias?
So the bias is just another parameter of the model. It's just another weight. It's also randomly initialized, and the model will learn the optimized value for the biases as well. It's not something you choose. You can choose it initially, which is based usually randomly, and the model will learn the actual bias as just a normal parameter.
That's why when you're doing the back propagation of the network and when you're trying to see how much of the weight, if you actually try to optimize the weight, how this optimization can actually affect the error that you get in the end, this is actually happening to the bias as well. So it's not only on the weights, but I mean, it's happening to the bias. You try generally to optimize all these values in order to be able to get the ultimate result that you want and the less error function that you can get in the end. The less error, let's put it like that.
The next question that we have is, how will you select training set and validation set from the data set?
Generally, I think I mentioned that in the slide, is 80% to 20%. So the way that you mixture and what you will be using for the training and what you will keep as a validation set, it has somehow to have this percentage, 80% for training and 20% for validation, and depends also on your data set, how small or big is your data set. But this is a rule of thumb generally when you're training your model, that you have an 80% training and a 20% validation.
So are there any other questions from the participants?
Maybe they can have an offline chat also, Dr. Anushya.
Yeah.
Thank you, Dr. Anastasia and Reda. Thank you for joining us. And I think our participants would have been highly benefited out of your speech. Thank you very much. Now we'll go to the last session of our FDP. We would be sending you the feedback link, and our feedback link is actually associated or linked with your e-certificate. So once you fill the feedback link, you will automatically get the e-certificate. Dr. Jenkins will explain how he will send you the feedback link. Now, if you want to give any live feedback about the FDP, you are always welcome. Maybe another 5 minutes we can have for any live feedback from you people. Anybody interested to give, you can come quickly. Okay. I think, shall we close the session? Maybe you can give the feedback offline also. Dr. Anushya, can you give the formal vote of thanks?
Yes, sir. So as we've come to the close of the faculty development program, Dr. Jude, Dr. Jenkins, and I would like to take this opportunity to extend a heartfelt gratitude to all those who made this program a success. So first off, we thank the Lord Almighty for giving us the chance to organize this event and for guiding us and helping us carry it out successfully. We would like to thank our management for enabling us to conduct this program, and also the head of our department, Dr. D. Nirmal, for his support and encouragement in organizing this event. We are incredibly grateful to our guest speakers, Dr. Anastasia and Mr. Rida today, and also to our speakers from the previous days, Dr. Anand Nair, Dr. Clement Christopher, Dr. Varun Gopi, and Dr. Uttu Kose. They have all taken time off their schedule to prepare for these sessions, and they've spent time with us, enlightening us on different aspects of deep learning. And they've all also very patiently answered all the questions that were posed to them. So we are very, very grateful to them for their time and effort. We also thank our colleagues from the Computer Technology Center of Karunya, especially Mr. Christopher. So since this event was an online one, they were instrumental in ensuring that everything went on without a glitch. And finally, we would like to thank all the participants for joining us these 5 days and for cooperating with us and entertaining our requests. A special shout out to our participants from outside India. We've actually had participants from Malaysia, Singapore, Saudi Arabia, Rwanda, South Africa, Canada, Germany, and Turkey. So thank you very much for joining us despite the time difference. And so thank you again to all our participants. We sincerely hope that the FDP was to your satisfaction, and we hope that it was useful. Thank you.
Thank you, Dr. Anushya, and thank you, participants. We will keep in touch. Not only the technical knowledge we get when attending FDP, it is all about making friends, research friends for further collaborations also. Thank you very much for choosing our webinar and being with us for the past 5 days. A special thanks to Dr. Anastasia and Reda. Hope we'll have some fruitful collaborations. Thank you. Thank you.